Okay, welcome to a little kind of mini unit. It is still a forces topic, but it's different enough that we separated it out from the main forces unit into something else. We're going to be talking about gravitation, and you might say, well, we already learned a lot about gravity, okay? We have already talked about how to find the force of gravity for objects that are on Earth. That's what we've always found the force of gravity for. And we know that the equation is Fg, it's a symbol for force of gravity, equals m, the mass, times g, the acceleration due to gravity. But that's specifically, even if we didn't talk about it like this that much, that's very specifically only for objects that are on Earth. And that's the force of gravity between those objects and the Earth itself. We now are going to talk about how to find the force of gravity between any two objects. And this is going to give us a new equation that is known as the Universal Law of Gravitation. How any two objects interact with each other through the force of gravity. Now, we did a lab about this, and you saw that there are three quantities that can affect the force of gravity between these two objects. Here they are. The first is the mass, well, I guess the first two are really the same thing. The mass of the first object, which we are going to call m1, and also the mass of the second object. Okay, remember forces are interactions between two objects, so we need two different objects here, not just one. And the last factor is the distance between the centers of these masses. And that gets the symbol R. During the course of the lab, we kind of worked out that these are the factors, and we saw how they affected the force of gravity. Specifically, we saw that the force of gravity was proportional to either mass. Therefore, if either mass changes by a certain factor, the force of gravity changes by the same factor. In other words, if one mass doubles, then the force of gravity between the two masses doubles. If one of the masses is it's now 1/3 of its original mass, the force of gravity is now 1/3 of the original. And in addition, we saw that if you change both of the masses, the force of gravity changes by the product of those two factors. So for instance, if you triple one of the masses and quadruple one of the others, then we saw that the force of gravity changed by, tripling is 3, quadrupling is 4, 3 times 4 is 12. The force of gravity was 12 times as big. It's a little more complicated to explain what happens with the force of gravity and the distance between the center of masses. The mathematical explanation is the force of gravity is inversely related to the square of the distance between the center of each mass. And again, we kind of already said this, the symbol is R. In other words, if the distance changes by a certain factor, the distance between the two objects, then the force of gravity changes by the inverse, or reciprocal, if you want to think of it that way, of the square of that factor. We looked at two specific examples. We looked at what happened if the distance doubled between masses. And in that case, we saw that the new force of gravity was 1/4 of the original. Now that makes sense because doubling the distance means multiplying the distance by 2. We take that 2, that extra factor of 2, we square it, 2 squared is 4, and then we take the inverse, we get 1/4. So it makes sense that if you double the distance, the force of gravity will only be 1/4 as big. On the other hand, if you halve the distance, if you cut it in half, you can square that half, that's the factor that changed by, you get 1/4, then you take the reciprocal, you get 4. And in this case, it doesn't matter the order that you do it in. You could even take the inverse of the factor and then square it. The order doesn't end up mattering. Okay? But that's how the force of gravity is related to these factors. We also made some graphs. We saw that the force of gravity, if you make a graph of force of gravity versus mass, it is linear. And we saw that if you make a graph of the force of gravity versus r, versus the distance of separation, you get something that looks like this. And that is known as an inverse square law graph. Okay? So those two graph shapes are pretty important. Based on all of this, we can establish a proportionality. Not an equation yet, but a proportionality. it would look something like this. We got done saying that if you change both the masses, then the force of gravity changes by the product of the factors of change. So that kind of implies that the force of gravity is proportional to m1 times m2. And we said that if it's inversely related to the square of the distance, then that means that if r is a symbol for distance, we can put it on the bottom and put a square on it, and therefore Fg is proportional to 1 over r squared, inversely proportional to the square. Proportionalities are great, but they're not as useful as a full equation. Okay? We can't actually calculate forces of gravity just from proportionality. We can see how the force of gravity would change, but we can't find an actual number. To be able to write an equation, we need to determine if there is some sort of constant in this equation that everything else is getting multiplied by. And there's actually a way to do this, and I'm going to use a simulation to do this. There's a real tricky way to do this. We're going to set m1, m2, and r all equal to 10. And if you think about what would happen if we did that, if m1 is 10 and m2 is 10, multiplying them together, you get 100. If r is 10, we got to square that. 10 squared is 100. That means that this will cancel out. Whatever is left, if we make the force of gravity, if we make the masses 10 and the distance 10, so 10 kilograms here and here, and then 10 meters here, whatever is left should be equal to some constant that we could throw in right here, and then we could multiply, and then that constant would allow us to write an equation instead of just a proportionality. Okay? We're going to write an equation. That's what we're doing here is we're trying to write an equation that looks like this. Fg equals, here's your m1 and m2 and then over r squared, but there's going to be a constant out front. If these things all cancel out, then whatever's left over equaling Fg should be equal to this constant that I'm going to call big G, and there's a reason I'm going to call this, because that's what we actually call this. Okay? This is a constant, and it's in the reference tables, and we will look at it in just 1 second. Okay? So if we go to the simulation, I actually already have it set up. We have a mass of 10 kilograms here, a mass of 10 kilograms here. The two masses are 10 meters apart. And if you look at that force on m1 by m2, we have 6.67 times 10 to the negative 11th newtons. So that's interesting. Remember that number, 6.67 times 10 to the negative 11th. Okay. So just to reiterate, this is the equation, the form of the equation. We set m1, m2, and r to equal 10 with their respective units. And we ended up with a force of gravity of 6.67 times 10 to the negative 11th newtons equals, remember this number G, I'm not really quite sure what that is yet, but mass 1 was 10 kilograms, mass 2 was 10 kilograms, and R was 10 meters squared. We know that all that's going to cancel out. Okay, or at least the numbers will cancel out, let's put it that way. So actually, let's go one step further. Let's write it like this. 6.67 times 10 to the negative 11th. Let me make sure you guys can read this. Okay, good. Newtons equals G. Up top, there's 100 kilograms squared. On the bottom, there's 100 meters squared. The hundreds will cancel out. If I want to solve for G, all I've got to do here is multiply the units up. The meter squared is going to multiply up right next to the n. The kilogram squared is going to divide down. This gives me a value for G of 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Now that sounds like a huge handful, but remember it's a constant, so they can look a little strange. Okay, so we've just found, because we set the masses and the distance to something useful, something kind of tricky, we found the value of the constant that should go in that equation. The constant must be, and I'm just going to write it again, 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. This number has a special name and a symbol. Matter of fact, it's right on the front of the reference table. It's the very first thing you read. Universal gravitational constant, big G, 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. So it is known as the universal gravitational constant. Universal meaning it applies everywhere. Our acceleration due to gravity that we've used, 9.81, that only applies on Earth. And besides, that's an acceleration. This is not an acceleration. The units are not that of acceleration. This is something different. Okay? This is a number that makes an equation work. That's what a constant really is. And again, it's written as capital G. By the way, on your reference tables, about halfway down the back, this is the equation we just derived. Fg, the force of gravity, is equal to G m1 times m2 over r squared. Okay? So the equation we just derived is legitimate. It is used for calculating the force of gravity between any two objects. You can still use this in a rearranged form, Fg equals mg, but that is very specifically for cases where the Earth is one of the objects and the other object is resting on Earth. That's when we use this. So for like 95% of cases, that's fine to use. But if one of the other objects is not, if one of the objects in your pair that the force of gravity is between is not Earth, or if the object that isn't Earth isn't directly resting on Earth or like very close to the surface, you use this equation. A couple of notes before we get to the examples. The force of gravity is always attractive as long as objects have mass. Any pair of objects will be attracted toward one another by the force of gravity. So there's no such thing as gravity being repulsive. It doesn't repel other objects away from, the force of gravity doesn't repel objects from each other. First example, determine the magnitude of the force of gravity between two people of mass 65 kilograms who are standing 2 meters apart. So you think, can I use Fg equals mg? Neither of the objects that we're talking about, the two people, is the Earth, so no, we can't use Fg equals mg. We have to use this. Fg equals big G m1 m2 over r squared. Big G is that constant, universal gravitational constant, 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Yes, you do have to write the units each time. M1 is 65 kilograms and M2 is also 65 kilograms. Squeeze that in. And R, the distance between the centers of the two objects, they're standing 2 meters apart. So 2 meters. Do not forget that this R is squared. You have to put the squared there. Make sure that you understand how to type in scientific notation on your calculator. Everyone's calculator is different. If you have one like mine, then I'll show you right now. But if you don't have one like mine, that's fine. You don't have to go get a new one, but please make sure you know how to type in scientific notation. It's a little different on every calculator. If you're not sure, either look it up online or ask me or figure it out yourself. Okay, but you have to know how to use your own calculator. 6.67, I'm going to hit, instead of doing like times 10 and then raised to the negative 11th, I'm just going to hit this EE button. EE stands for the phrase times 10 to the. So I do 6.67 times 10 to the negative 11th. There we go. Times 65, divided by 2 squared is 4. I get 0.0000007, which is 1, 2, 3, 4, 5, 6, 7, 8. 7 times 10 to the negative 8 newtons is the force of gravity. Even two people standing 2 meters apart, average sized people, there is a force of gravity between them, an attractive force of gravity. It's very, very small, but it is there. How does the force of gravity compare to the above if they stand 4 meters apart? Well, there's a couple ways we could do this. The first way, which I think involves too much calculation, is to write this entire thing over again and just put a 4 down here instead. That's fine. You'll get the right answer. I hope you don't make a calculation mistake, okay? Because that would be a lot of work for getting the wrong answer. Instead, what I'm going to show you is something that involves less calculation, but a little bit more thinking. I'm going to show you how to do this algebraically. I'm going to write this down. I'm going to write down FG, I'm just going to put a little 1 down at the bottom, equals G M1 M2 over R1 squared. Now, the 1 is a subscript. Both these ones are subscripts, which means I'm not putting a new variable in. I'm not like saying you have to multiply by an additional thing. It's just to differentiate it from up here. The 1 just means that something a little different is going on. The people are now standing 4 meters apart. Before, up here, they're standing 2 meters apart. So what I'm going to do is relate R1 to the original R. Originally it was 2. R1 is 4. So R1 must be twice the size of the original R. I'm going to plug that in. G is the same. That's a constant that never changes. M1 and M2 are the same. But instead of writing R1, I'm not going to do 2R in parentheses, that's very important, squared. It's very important you put parentheses here, because if you just wrote 2R squared, what that says is that you've got R squared and you're multiplying it by 2. That's not what we're doing here. This distance of separation is what's getting squared. If you write it like this, you're acknowledging that the distance of separation is twice as big as it was, and then it has to get squared in the context of the equation. Okay? If you do it the other way, if you don't write a parentheses here, you're going to make a math mistake. You're going to square the original distance between the objects and then double it by 2, and you will not get the right answer. So I just made a huge deal about putting this in parentheses. Well, now we're going to evaluate this. We're going to square this entire thing on the bottom and get rid of the parentheses. G, M1, M2. If I take 2R in parentheses and I square it, I should get 4R squared, because I square the 2 and I square the R. I want you to look at this that I've got kind of bubbled in or dashed in right there. My whole expression is G M1 M2 over 4R squared. But if I leave out the 4, then it's just G times M1 times M2 over R squared. If you think about it, that should look familiar because it's the exact same equation that we started with up here. Fg, the original force, is equal to G times M1 times M2 over R squared. That's showing up right here. That means that I could rewrite this as just being equal to the original Fg. I've got a 4 on the bottom here. So that means a 4 on the bottom like dividing something by 4 is the same as multiplying by 1/4. I'm going to change this to 1/4 times Fg, times the original. Okay? All I'm doing is rewriting this in a slightly different format. I'm taking the 4 out and I'm making it 1/4 because it's a 4 on the bottom. And I'm making G times M1 times M2 over R squared equal to Fg, the original Fg, we should say. The original Fg was 7 times 10 to the negative 8th. So what this is saying is that the new force of gravity, based on like how the algebra worked out, based on the fact that this radius, or not this radius, this distance between the objects doubled, the new force of gravity should be 1/4 the original. 1/4 of 7 times 10 to the negative 8th newtons, so divided by 1/4, is approximately 1.8 times 10 to the negative 8th. And that's with some rounding, obviously. But I just did that entire problem by making one calculation. Okay? The only calculation I did was I took the original force of gravity and I modified it based on the factor that came out when I made the changes to one of the variables. You can do it the other way. You can plug in a 4 here and go through all the calculation. Okay? But there's a much bigger chance of making a calculator error if you do that. Plus, I know this took longer this time. Once you get used to this method, it is much, much, much quicker than doing it the long way. You got to trust me on that one. Let's get some real numbers in here. Calculate the force of gravity between the Earth and the Moon. On the front of the reference table, about the 5th entry down to the, let's see, that would be the 10th entry down, we have some masses and radii and distances that are useful for this unit. Mass of the Earth, mass of the Moon, mean radius of the Earth, so average radius of the Earth, average radius of the Moon, average distance from Earth to Moon, average distance from Earth to Sun. we want the force of gravity between the Earth and the Moon. So I'm going to start with Fg equals G m1 m2 over r squared. G is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. M1 and M2 are going to be the masses of the Moon and the Earth. That's the 5th and 6th entries on our table. Mass of the Earth is 5.98 times 10 to the 24th kilograms. Mass of the Moon, 7.35 times 10 to the 22nd kilograms. R is the distance between the objects, not the radius of either object, but the distance between the centers of the object. Earth to Moon, 3.84 times 10 to the 8th meters. Please do not forget, because it's the easiest thing to forget, that this bottom part has to be squared. So, again, here's where you have to know how to type in the numbers in scientific notation. 6.67 EE negative 11th times 5.98 to the 24th times 7.35 to the 22nd. That's what I get up top. You can do this next part two different ways. You can either divide by 3.84 times 10 to the 8th twice, because that's what this is. It's 3.84 times 10 to the 8th times 3.84 times 10 to the 8th. So you just divide by it twice. Or you learn how to use parentheses. I do divide by, in parentheses, 3.84 times 10 to the 8th squared, and the parentheses, now that's the bottom, and once I hit enter one more time, now I've divided the top by the bottom, and I see that the force of gravity is, between the Earth and the Moon, 1.99 times 10 to the 20th newtons. Okay. And I do want to make one point. So this force of gravity between people was tiny. Force of gravity between planets or stars or big objects is huge. It's absolutely enormous. Okay. So the force of gravity is typically very small for what we would call normal-sized objects. And then, as we set up here, either you do the math all over again, or use the algebraic method, which we demonstrated here. And a matter of fact, that's what we're going to demonstrate down here as well. How would the force of gravity change if the Moon were 3 times as massive and the Earth were twice as massive? So what we're going to do here, I'm going to do FG, and I'm going to call it A, because I don't want to have too many numbers flying around. We're saying that the Moon is going to change its mass and the Earth is going to change its mass. Or we're hypothesizing what would happen if the masses were different. So I'm going to label this like this. G, M1A, M2A. That's just a label to show, hey, the masses are going to be different over R squared. If the Moon, okay, so the Moon was the second one. So this is going to be M2A. Is, let's see, 3 times as massive, so it's 3 times as big as M2 was initially, and the Earth were twice as massive, so that means M1A is going to be, let's see, 2M1. Okay, so the Moon, the new mass of the Moon is 3 times as big, new mass of the Earth is twice as big. I'm going to plug those changes in here. Again, all we're doing is relating the new mass of the Moon, the A is just a subscript, don't get freaked out about it, to the old mass of the Moon from the original problem. So I'm going to do G. M1A is now twice the original. M2A is 3 times the original. And R stayed the same. It didn't say anything about changing that. One of the nice things about multiplication is the order doesn't matter. So the fact that I have a 2 and a 3 here, I can pull those all the way out to the front and multiply those together. 2 times 3 is 6. That gives me 6 G M1 M2 over R squared. Look right there. G M1 M2 over R squared is exactly what I had initially. What this shows me is that the new force of gravity is 6 times the original force of gravity. So that's 6 times 1.99 times 10 to the 20th newtons, which is FGA for the new force that we're trying to figure out here, 1.19 times 10 to the 21st newtons. And that makes sense because that's 6 times as big, and we talked about earlier how if the masses both change, the force of gravity changes by the product of those factors. Moon's 3 times as massive, Earth is twice as massive, multiply 3 and 2, you get 6. The new force of gravity is 6 times as big, and that's exactly what happens here. This is just a more formalized way of showing that work algebraically if you were asked to show the work. We're going to get to some more examples, but before we do so, we do have to talk about one last little topic called gravitational fields. The force of gravity is weird in the sense that every other force that you have talked about so far requires contact. Normal force, spring force, tension, friction, applied force. All of those are contact forces. The force of gravity is not. The explanation for it is a little weird. Any object that has mass literally warps the space around it. That warped space, that changed space, is known as a gravitational field. You can think of it as the object with mass affecting the space around it and causing other objects with mass to sense this affected space. We call these gravitational fields. The pictures of gravitational fields will show the direction of the force of gravity at different points near an object by using vectors. So what we're trying to show here is just what the gravitational field looks like. You just need to really know what the picture looks like in general. It's like maybe one multiple choice question. I'm going to show you 2 different pictures. We're going to do one picture of Earth as if we're taking it from up close. And by up close, I mean like fairly close to Earth's surface. Like here's the curve of Earth's surface. The gravitational field would look something like this. All of the vectors representing the direction of the force of gravity at that point would be pointing not straight down necessarily, but towards the center of the Earth. You can see how they're all not pointing straight down, but towards the center of the Earth. I'm also going to add in some other vectors that are a little smaller to show that the strength of the gravitational field changes as you go away from the mass. The smaller vector means the field is weaker there. So, I mean, the converse of that is that the gravitational field is stronger closer to Earth. Let's say you're looking at Earth from far away. The gravitational field will look like this. Okay? And this is, I think, pretty obvious. All the arrows representing the direction that the force of gravity would pull objects in point straight towards the center of Earth. Your job with gravitational field pictures is just to recognize what the gravitational field looks like. When we come back, we'll just run through a whole bunch of examples of how to use the Universal Law of Gravitation to solve problems. Talk to you later.